But getting back to the BECs, so what are some of its properties? I mean, beyond the fact that there are four regularly observable states of matter. I just did an episode with a plasma physicist, Ian Hutchinson of MIT. So we've talked all about plasma, but there's plasma, gas, solid, liquid. That's what we typically observe in day-to-day life. And this is not one of them, since BECs don't live at room temperature.
Yeah. I mean, so we call it a macroscopic quantum state. And what we mean by that is that when you get these atoms and you get them cold enough, they condense, they fuse together into a so-called BEC. But that's really a giant quantum wave function is the configuration they take. And so, then that's really what's interesting about BEC is, it's kind of curious that it forms, but what's really interesting is just the behaviors of its properties. And it's sort of worth noting that Einstein was just working with the equations, and he predicted that this would occur, this condensation. But then he just completely overlooked that it would have these really interesting properties. And so, and I like that as an example of just showing smart people don't notice everything. And so these interesting properties are, like I say, that the condensate is this sort of giant quantum wave function where giant is still pretty small, but it's, getting up to the size of a hair. And so very easily seen with a microscope, whereas most wave functions are millions of times smaller than that, where you can never observe them directly. And so in the BEC, you can kind of observe and manipulate the quantum states in a very direct way, and play games with it. And that's really what makes it interesting.
Mm-hmm. So how cold are we talking? One.
So to form it originally, it gets down to about a tenth of a microkelvin. So that's a tenth of a millionth of a degree above absolute zero,
which is as cold as it gets.
Yeah, I mean, we actually in later experiments got down to about 1 nanokelvin, which is a billion, 1 billionth of a degree above absolute zero. And yeah, that's as cold as it gets. And in fact, nothing really interesting happens once you get colder, because as you get colder, it just means that a bigger fraction of your sample is in the Bose condensate. And you're already, once you got most everything in the condensate, that's nothing interesting after that happens.
This is speculative, not physically interesting. But as I was reflecting on the BECs, my understanding is this is so cold that this temperature is never reached in nature. So Bose-Einstein condensates don't occur naturally. And it's fascinating to think that over the entire lifetime of the universe and the future, physics predicts things that can happen, entire states of matter that would just never occur if it weren't for humans or other intelligent life around Alpha Centauri making BECs.
Yeah. No, I mean, I agree, because we know the coldest place in nature is sort of, interstellar space, and that's 3 degrees above absolute zero from the radiation left over from the Big Bang at the formation of the universe. And that's millions of times too hot. And so, that is sort of a cute thing about BEC, is it's can only exist because of human ingenuity.
Mm-hmm. And then, let's see, what if it's possible to describe what it is like visually to inspect this borderline macroscopic with a microscope wave function? What are the sorts of behaviors that you're witnessing that outside of a BEC are just not possibly perceptible?
Well, I mean, what we look at is actually not that exciting. I mean, we just look at shadows, and so you shine light on the thing, and you take it, and it absorbs that light and makes a shadow, and we image the light beam that's going by and see a shadow that gives you the shape of the BEC, and so. It's just a little dark region in a beam of light. So, that's not really that exciting. But then the shape of that shadow and how it changes under different conditions and how it interacts with other things, that's really the things we're looking at.
I see. I saw that there are like vortices of a sort. I saw that the other experimenter, I think his name was Wolfgang Ketterle at MIT, who produced a BEC a few months after you. He also, you know this, but our listeners don't, that he received a third of the Nobel Prize share. Your collaborator, Eric Cornell, got the other third. And he observed in his sample, and I think he still works on them very much so, wave interference patterns, like, I mean, of the sort that are very well known even in the zeitgeist with like the twin slit experiment, that sort of thing.
That's right. Yeah, you can take condensate and put it back together in two pieces, and it forms an interference pattern, which is some kind of rather striking when you think about it, sort of making atoms go away or canceling out their existence, and that starts to seem pretty strange.
Right, where they behave like a wave when you expect them to behave like particles, and it really, I mean, that's what the philosophers of physics are still wrapping their minds around 100 years later. But now, beyond the bare feat of experimentally confirming a 75-year-old theoretical prediction made by Einstein, of all people, and I suppose we also have to throw in the sheer interest for a physicist of this macroscopic wave function. What was it about this problem in particular that made it so interesting to you as a physicist that you were really intent on producing the BECs? Or maybe that those two things encapsulated it?
Yeah, they pretty much encapsulate it. It was labeled as the holy grail of atomic physics because people have been trying to get it for so long. So, just being able to make it was nice. But then we could study its properties and how it behaved under different conditions, and then it allows you in particular to, since it is sort of this giant quantum mechanical system, it allows you to explore the transition between what we talk about as kind of the microscopic quantum mechanical world and the macroscopic classical world we live in now. And, people kind of knew what happens at each extreme, but not nearly so well what happens in that intermediate region. And so a lot of the experiments with BEC were sort of probing that region and sort of with kind of essentially big quantum mechanics and what happens in that intermediate area.